So, as philosophers, we often think about those like ideal models of decision making, right? The ones based on perfect logic and beautifully consistent preferences.
Yeah, those elegant frameworks that tell us how we should choose.
Right, exactly. But then, like, what happens when we actually look at how people really decide, out in the messy real world, especially when faced with uncertainty?
That's where descriptive decision theory comes in.
It does, doesn't it? It's like shifting that focus from, the normative to the descriptive.
Precisely. From how we ought to choose to how we actually do choose.
With all our like human quirks and cognitive biases and all that.
Exactly. All that messy, wonderful complexity. And that's what we're diving into today.
We are. And our guide for this deep dive is the descriptive decision theory entry from the Stanford Encyclopedia of Philosophy.
A great resource, really comprehensive. It starts by laying out that foundational model, the subjective expected utility model, or SEU.
Right, SEU. The gold standard, or at least the starting point.
The benchmark, yeah. And then it goes on to explore all the ways in which empirical observations have shown that, well, people don't always behave the way SEU says they should.
They don't, do they? Which, for philosophers like us, I think is where things get really interesting.
Absolutely.
Yeah.
Because it forces us to confront, the gap between our idealized models of rationality and the actual reality of human behavior.
Right. It's like, how do these deviations from the ideal inform our understanding of what it even means to be rational?
Big questions, for sure. And that's really the mission of this deep dive, right? To unpack the key aspects of descriptive decision theory and see how it challenges those traditional philosophical assumptions about rational choice.
Okay, so let's start with that foundational model, that SEU framework. It's the one that emerged from like the work of Savage, De Finetti, Ramsey von Neumann, and Morgenstern, some pretty heavy hitters. What's the basic idea behind it?
Well, at its core, SEU posits that individuals they act as if they're going through this like two-step process. First, they assign numerical values, what we call utilities, to each possible outcome.
So basically, how much they desire or value each outcome.
Right, exactly. And then second, they assign subjective probabilities to the occurrence of those outcomes.
Which basically represents their belief or confidence that those outcomes will actually happen, given their choices.
Yeah, and these subjective probabilities, they can align with objective probabilities if those are known, but crucially, they don't have to.
And then the theory goes, we make our choices by trying to maximize that subjective expected utility.
Right, which is essentially like a weighted average, For each possible action, we multiply the utility of each outcome by its subjective probability.
And then pick the action with the highest total sum.
Precisely. Now, of course, there's that that ongoing philosophical debate about whether people actually have these internal states of belief and desire.
Right, like are these utilities and subjective probabilities real psychological entities or just, convenient mathematical constructs?
The ontologically bolder interpretation versus the instrumentalist view.
Exactly. And then there's that whole thing about representation theorems.
Oh, right. Those fascinating results that show how the entire SEU framework with its utilities and probabilities can be derived from a set of seemingly basic axioms about preferences.
So, like, if our preferences have these certain, consistent properties, then they can be represented by the SEU model.
Precisely.
And a lot of the testing of SEU really comes down to, like, examining whether people's preferences actually line up with those underlying axioms, right?
Yeah, if we see like systematic violations of those axioms, then it casts doubt on the descriptive accuracy of SEU.
Okay, so let's dive a bit deeper into those axioms. The entry focuses specifically on Savage's framework for SEU.
Right, Savage. He lays out this very precise framework where the basic building blocks are acts, states, and outcomes.
Okay, so an act is like the choice you make. A state is some condition in the world. And the outcome is what results from your action in that specific state.
Exactly. And he also introduces these constant acts, which always lead to the same outcome no matter what the state is.
And then events are just sets of states.
Right. And he uses that, that standard notation for preferences, the symbol, to mean is at least as desirable as.
From which we can get strict preference and indifference.
Right, right. And he even extends that preference relation to outcomes themselves by saying that one outcome is preferred to another if the constant act yielding the first is preferred to the constant act yielding the second.
Okay, so that's the setup. What's the main result of Savage's representation theorem? Like, what's he trying to prove?
He's trying to show that if an agent's preferences over acts satisfy certain fundamental principles, his axioms, then those preferences can be represented by a utility function over the outcomes and a subjective probability function over the states.
And the key point is that the utility function is unique up to a positive linear transformation, while the subjective probability function is actually unique.
Right. And the overall utility of an act is then calculated by, summing the utilities of all the possible outcomes, each weighted by the subjective probability of the state that leads to that outcome.
Which is captured formally in equation 1 in the text.
Right. And to get to that result, he lays out several key axioms. The first one, weak order, which includes both transitivity and completeness, seems, pretty fundamental to any coherent theory of choice.
Yeah, transitivity means if you prefer A to B and B to C, then you got to prefer A to C. Completeness means for any two options, you either prefer one or you're indifferent.
Right. Without those, our preferences would be all over the place, totally chaotic.
Couldn't make decisions even if you wanted to. Then there's the sure thing principle. This one seems really intuitive, especially when we're thinking about, decisions under uncertainty.
It is, yeah. It basically says you should ignore the states where two different actions lead to the same outcome.
Because those states don't really differentiate between your options, so they shouldn't influence your preference. The notation AAAAAIGI captures that really well.
It does, yeah. Basically, if you prefer act to act G when they both have the same consequence, if event A happens, then your preference shouldn't change, even if the consequence when not happens changes from, say, to something else.
Okay, and the third key axiom that's relevant here is weak comparative probability. This one tries to, connect our preferences to our beliefs about the likelihood of events.
Right. The intuition is that if you prefer getting a better outcome if an event happens compared to a worse one, and you have the same preference when those outcomes are conditional on event, then that difference should reflect your belief that A is more likely than B.
The axiom formalizes this with two pairs of outcomes, a preferred to and two events, and to 4A.
Right, so your preference between getting one of two otherwise versus getting one if B and otherwise should mirror your preference between if A and otherwise versus if B and otherwise.
Suggesting that there's this, underlying judgment about the relative probabilities of A and B.
Right, exactly.
Now, the entry also mentions a few other technical conditions, like non-degeneracy, small event continuity, and event-wise monotonicity. I don't think we need to get into the weeds with those, but they are, important for the formal structure of Savage's theory. So how does Savage actually derive that SEU representation from all these axioms? What are the key steps in his proof?
Well, he starts by introducing this idea of subjective comparative probability, denoted by A on RHDB, which holds if and only if, whenever you prefer getting a better outcome given over a worse one, you also prefer getting that better outcome given B over the same worse one.
So it's like a way to compare the likelihood of events based on your preferences.
Right. And using his axioms, he shows that this comparative probability relation on RHD behaves like we expect probabilities to behave.
Okay.
And the small event continuity axiom ensures that we can actually represent this qualitative ordering with a unique quantitative subjective probability function. The sure thing principle is also crucial here, especially with weak comparative probability, because it allows him to prove that this probability function is additive.
So he's got subjective probabilities. How does he bring in utility?
Right. Well, the key link comes through this idea of state neutrality. This shows that if two acts assign the same probabilities to the same outcomes, no matter which states lead to those outcomes, then the agent should be indifferent between them.
Meaning it doesn't matter how you get to those probabilities, only what those probabilities are.
Exactly. And because we can always conceive of some act that gives us any particular probability distribution over outcomes, state neutrality lets us shift from preferences over acts to preferences over subjective lotteries.
Which are just probability distributions over outcomes without worrying about the states.
Precisely. And then by using his axioms again, he shows that these preferences over lotteries have to satisfy three properties: mixture weak order, mixture continuity, and the very important independence axiom.
Hold on. Let's pause there for a second because that independence axiom is going to be like a major point of contention later on.
Oh, it is, yeah.
So what does it say exactly?
It basically says that if you prefer lottery to lottery,
Hmm.
then you should still prefer even if you mix them both with some third lottery using the same mixing weight.
Like if you add some common element to both options, it shouldn't change your relative preference between them.
Right, that common element should be independent of the original preference. Formally, it says that P CoBEF plus, if and only if lambda PF plus 1 lambda, for any mixing weight between 0 and 1, and for any lottery.
Okay, I think I'm following. And this is where Savage's work connects with like the earlier work of von Neumann and Morgenstern, right?
Yes, exactly. They had shown that if preferences over lotteries satisfy those three properties we just mentioned, then those preferences can be represented by an expected utility function.
Where you just sum up the utilities of each outcome, weighted by their probabilities.
Precisely. So, by showing that his axioms lead to preferences over subjective lotteries that satisfy those same properties, Savage basically completes his representation theorem, linking preferences over acts to the maximization of subjective expected utility.
Beautiful, if a bit complex.
It is, yeah. But the entry then introduces this helpful visual tool called the probability triangle.
Oh, right. That's a good way to like visualize preferences over lotteries when you have just three possible outcomes.
Exactly. Well, you see, you have a best outcome, a middle outcome, and a worst outcome. Any lottery over those three outcomes can be represented by a point in this equilateral triangle.
And the position of that point is determined by the probabilities of the best and worst outcomes.
Right, because the probability of the middle one is just, one minus the other two.
Got it. So how does SEU work within this triangle? Like what do preferences look like geometrically?
Well, under SEU, we get some very specific predictions. First, we have stochastic dominance, which means that if one lottery always gives you at least as good an outcome as another, and sometimes strictly better, you should always prefer that first lottery.
Seems reasonable.
Yeah. And in the triangle, this means preferences increase as you move towards the top for higher probability of the best outcome and towards the left for higher probability of the middle outcome. Also, the indifference curves, which connect all the lotteries the agent is indifferent between, are predicted to be upward sloping, linear, and parallel to each other.
The steeper the slope, the more risk-averse the agent is.
Right, exactly.
I'm picturing figure 1 from the entry in my head right now. But here's the thing. Despite all its elegance, SEU doesn't perfectly describe how people actually make decisions. And that's where the work of Allais and Ellsberg comes in, right?
Yes, absolutely. They really exposed some of the descriptive shortcomings of SEU.
Let's start with Allais and his paradoxes. These were like direct challenges to that independence axiom we talked about.
Right. Allais, he designed these clever choice scenarios that revealed systematic violations of independence. The most famous one is the common consequence problem.
Okay, remind me how that one works.
He gave people two pairs of lotteries. In the first pair, you could choose between a sure, moderate outcome or a gamble with a high probability of a much better outcome but a small chance of getting nothing.
Okay, got it.
And in the second pair, he adjusted the probabilities, but he kept the basic structure the same, with a shift in a common consequence.
And what did he find?
He found that a lot of people preferred the sure thing in the first pair, that guaranteed moderate outcome. But then in the second pair, they switched and chose the gamble, even though the change in probabilities was essentially the same.
So they were being inconsistent with how they valued that change in probability.
Exactly. And this pattern of preferences, which a lot of people find like intuitively compelling, goes directly against the independence axiom. Specifically, it violates the common consequence principle.
Which says that your preference between two lotteries shouldn't be affected by a common outcome they share.
Right, and the entry shows how this violation works formally by representing the lotteries as mixtures with common consequences labeled Q1 and Q3.
And it shows that if you prefer 1 to P2, then common consequence says you should also prefer P4, but people often don't.
They often prefer P1 to P3.
Right, which is exactly the Allais preferences. And figure 3 in the entry shows this nicely with decision trees.
Yeah, and figure 4 shows the problem in the probability triangle. Those line segments connecting P1 and P2 and P4, they're parallel.
And an expected utility maximizer should have parallel indifference curves.
Right, so they can't cross one segment from below and the other from above, which is what you'd need to accommodate the Allais preferences.
Got it. Allais also pointed out the common ratio problem, which is another issue with independence. The entry doesn't go into a lot of detail there, but it mentions that it also involves choices that map to parallel segments in the probability triangle.
Right, the common ratio problem basically presents another set of choices where people's preferences shift in a way that violates independence. And again, the fact that it involves parallel lines in the triangle highlights the conflict with those uh, linear parallel indifference curves of expected utility theory.
And all this wasn't just theoretical. Studies in the 60s and 70s showed that these LA-type violations were quite common.
They were, yeah. So clearly, SEU had some descriptive issues.
So how did theorists respond to these violations of independence? What were some of the theoretical fixes or alternatives?
Well, there were a few different approaches. One approach tried to, salvage as much of the SEU framework as possible. This led to the idea of probabilistic sophistication.
So still working with probabilities and utilities, but tweaking the way preferences are connected to them.
Exactly. They kept the idea that preferences over acts could be reduced to preferences over lotteries that satisfy mixture weak order, mixture continuity, and stochastic dominance, but they dropped the independence axiom.
Makes sense.
And to do this, they often had to, weaken the sure thing principle or strengthen weak comparative probability, like Machian and Schmeidler did with their strong comparative probability axiom.
So still using probabilities, but allowing for more flexibility in the indifference curves.
Right. Another class of models took a more drastic approach by directly relaxing that linearity assumption. Some of these models kept a weaker form of linearity called betweenness.
Which means that if you're indifferent between two lotteries, you're indifferent between any mixture of them.
Exactly. Weighted utility, or WU, is a good example of this. It modifies the expected utility formula by adding these outcome-dependent weights.
So instead of just multiplying the utility by the probability, you multiply it by some weight that depends on the outcome.
Right. And if these weights aren't constant, then you can get those fanning out indifference curves that can accommodate the LA preferences.
I can see how that would work visually, but the entry also points out that even betweenness, this weaker form of linearity, started running into empirical problems.
It did, yeah. Evidence suggested that even linear indifference curves weren't always a good fit. So then came models that dropped betweenness entirely. One important one is rank-dependent utility, or RDU.
RDU, that one sounds familiar. What's the basic idea?
RDU assumes that you first order the outcomes of a lottery based on your preferences. Then it introduces this probability weighting function that transforms the objective probabilities.
So you're messing with the probabilities themselves.
In a way, yeah. The overall utility is still calculated by summing up the utilities of the outcomes, but those utilities are weighted by these transformed probabilities.
And it's that probability weighting function that allows RDU to explain the LA paradox.
Right. If that function overweights small probabilities and underweights large probabilities, it can create the preference reversals that violate independence.
Okay, that makes sense. The entry also mentions cumulative prospect theory, which is like a generalization of RDU, and it brings in ideas like reference points and different weighting functions for gains and losses. And it says that RDU satisfies a weaker version of independence called ordinal independence. What's that about?
Ordinal independence focuses on the cumulative distribution functions, or CDFs, of the lotteries. It basically says that you should ignore any outcomes where the CDFs of the two lotteries are the same.
So if two options agree on the probability of getting an outcome that's no better than a certain value, that shouldn't influence your preference between them.
Exactly. And the LA preferences are actually consistent with ordinal independence. The entry mentions that you can even derive it from combinatonic independence, which we'll talk about with the Ellsberg paradox, if you assume probabilistic sophistication.
Okay, so that's a good overview of the challenges to independence. Now let's move on to Ellsberg and his three-color paradox. This one really gets at the question of, do we always have well-defined subjective probabilities, especially in situations where there's ambiguity?
Right. Ellsberg, he really highlighted how people behave differently when they don't know the exact probabilities. In his classic example, he described this urn with 90 balls. 30 are red, and the other 60 are either black or yellow, but you don't know the exact
We're in
split.
classic Ellsberg setup.
And then he presented people with bets on the color of a ball drawn from the urn.
And what did he find? What are the typical Ellsberg preferences?
Well, people typically preferred betting on red, where the probability is known 1/3, over betting on black, where the probability could be anywhere from 0 to 2/3.
So they preferred the bet with the known probability, even though the other bet had the potential for a higher probability of winning.
Exactly. It's a classic example of ambiguity aversion. But then when he framed the bets differently, like betting on not red versus not black, people often reversed their preferences.
So they were still going for the bet where the overall probability was known, even if it meant betting on a combination of colors.
Right, because knowing that there are 30 red balls lets you pin down the probability of not red more precisely.
I see. And this pattern, as the entry points out, violates a bunch of stuff. Savage's sure thing principle, strong comparative probability, even probabilistic sophistication.
It does, yeah. And it creates this logical contradiction. If you assume people both reduce these decisions to lotteries with subjective probabilities and order those lotteries by first-order stochastic dominance.
So ambiguity really throws a wrench into the SEU machinery. How did theorists try to account for this?
One approach was to move away from the idea of additive probabilities and instead use capacities, which are like non-additive probabilities. Choquet expected utility, or CEU, is a good example of this.
Okay, so instead of probabilities that add up nicely, you have these capacities that might not.
All right. In CEU, the value of an act is determined by a Choquet integral, which is similar to expected utility, but uses capacities instead of probabilities.
So, like in the Ellsberg urn, the capacity of black or yellow might not be the sum of the capacities of black and yellow separately.
Exactly. And this can model ambiguity aversion. Like the entry gives an example where the capacity of red is 1/3, the capacity of black is 0, but the capacity of black or yellow is 2/3.
Which reflects the fact that there are 60 non-red balls.
Right. And this explains why someone might prefer betting on red over black, but then prefer not red over not black.
Because not red has a higher capacity, even though it's a combination of events. The entry mentions that Gilboa and Wacker gave an axiomatization for CEU, and they used a weakened version of sure thing called commotonic sure thing. What does commotonic mean here?
Two acts are commotonic if they order the states of the world in the same way based on how good the outcomes are. Basically, they agree on which states are better or worse.
Okay.
And commotonic sure thing says that the regular sure thing principle only has to hold when the acts are commotonic.
And in the Ellsberg paradox, the acts aren't commotonic.
Right, like betting on red and betting on black. Those acts order the states differently.
So people's preferences can violate sure thing, but still be consistent with commotonic sure thing.
Which makes them compatible with CEU. Another way to deal with ambiguity aversion is to use multiple priors models, like maximum expected utility or MEU.
MEU. That one sounds interesting. How does that work?
MEU says that instead of having one subjective probability distribution, you consider a whole set of possible distributions, all consistent with your information.
So like in the Ellsberg urn, you'd consider all the possible splits between black and yellow ball.
Yeah, and then you evaluate an act by looking at its expected utility under each of those distributions.
And you pick the act that maximizes the minimum expected utility across all those distributions.
Exactly. So it's like playing it safe and focusing on the worst case scenario.
Very cautious.
It is. Yeah. And the entry mentions that CEU with a convex capacity is actually a special case of MEU. The CEU maximizer ends up acting like an MEU maximizer who's considering the worst case scenario over a specific set of probabilities.
Fascinating. But MEU seems like a really strong form of ambiguity aversion. Are there models that are like more flexible?
Oh yeah, for sure. There's alpha MEU, which lets you adjust the level of ambiguity aversion with a parameter, alpha.
So you can be more or less ambiguity averse depending on the value of alpha.
Right, and then there are models that use higher order probability distributions.
Probability distributions over probability distributions.
Yeah, basically you have beliefs about the likelihood of different probability distributions being the true one. The smooth model is an example of this. It uses a function to transform the expected utilities calculated under each possible prior distribution, and the shape of that function captures your attitude towards ambiguity.
Okay, so we've seen how theorists tackled the issue of ambiguity aversion. Now, let's move on to the last big challenge to SCU discussed in the entry, the issue of weak order, specifically transitivity and completeness.
Right, those fundamental assumptions that for any two options, you either prefer one, the other, or you're indifferent, and that those preferences are consistent.
And we talked about how those are really at the heart of SCU and most other decision theories.
They are, yeah. But there's been a lot of research looking at whether people's preferences actually are transitive and complete.
And it turns out sometimes they're not, right?
Right. A classic study by Amos Tversky in 1969 suggested that people might show intransitive preferences, where they prefer A to B, B to C, but then C to A.
Creating this like circular preference. How did he explain that?
He proposed this idea of barely perceptible differences. The thought was that when two options are really similar, people might focus on just one dimension, like the payoff, and ignore the small differences in probability. But when the differences get bigger, they start paying attention to those probabilities, and that's when you get the intransitivity.
Interesting. But the entry also points out that the evidence for truly intransitive preferences is still debated.
Yeah, it's not totally settled.
Yeah.
Some argue that what looks like intransitivity might actually be, some kind of error or just people changing their minds about what's important.
Makes sense. Then there's regret theory, developed by Loomes and Sugden. This theory is interesting because it actually predicts certain types of intransitivities.
It does, yeah. Regret theory is all about how we feel about outcomes in comparison to what could have been.
So, like, if you choose option A and it turns out badly, you might regret not choosing option B, which would have been better.
Exactly. And those anticipated feelings of regret or rejoice can actually influence our decisions.
So it's not just about the objective outcomes, but also about our emotional responses to them.
Precisely. They formalize this with the comparative utility function, or a regret rejoice function, that modifies the standard utility based on these comparisons.
And if you assume regret aversion, which means you really dislike those feelings of regret, then regret theory can predict violations of independence, like those Allais effects we talked about.
It can, yeah. And it can also predict those intransitive preferences. They have this example with 3 outcomes and 3 equally likely states that leads to a cycle of preferences.
So you prefer F to H and then back to.
Exactly. And because it's all about pairwise comparisons, regret theory can also lead to violations of state neutrality and even stochastic dominance.
Interesting. It does keep sure thing in betweenness, though, at least for independent distributions.
It does, yeah.
Okay, finally, the entry talks about the assumption of completeness, which is the idea that you can always say whether you prefer one option the other or are indifferent.
Right. And it's interesting because even von Neumann and Morgenstern and Savage himself had some doubts about whether this was always realistic.
They did.
They did, yeah. They acknowledged that there might be situations where people genuinely can't decide or don't have a clear preference.
Like when the options are really complex or maybe involve trade-offs across values that are hard to compare.
Right, exactly.
And how do you model that kind of indecisiveness?
Well, one way is to use multi-prior expected multi-utility models.
Okay, those sound complicated.
They are a bit, yeah. The basic idea is that you represent preferences as holding only if an option is preferred across all the admissible ways of evaluating it.
So, like, if there are multiple plausible probability distributions or utility functions that you might be using, and one option is better under all of them, then and only then do you prefer it.
Exactly. And if some ways of evaluating the options favor one and some favor the other, then your preference is considered incomplete.
Okay, I think I get the gist of it. So we've covered a lot of ground here, looking at all these ways in which human behavior deviates from SEU. But now the entry gets into a really crucial question, especially for philosophers: the relationship between descriptive decision theory and normative decision theory, the theory of how we ought to make decisions.
Right. Right. And Allais, he famously argued that his paradoxes didn't just challenge the descriptive accuracy of SEU, but also its normative validity.
So he was saying that SEU might not even be the right way to think about rational choice, even in principle.
Yeah. He argued that a good theory of rational choice should be logically consistent, sure, but it should also align with our intuitions about what's rational and with the behavior of people we generally consider to be rational.
And he felt that SEU didn't quite meet those criteria.
Right. He questioned whether the axioms, especially independence, were truly justified. And he pointed to the fact that people systematically violated them, suggesting that maybe those violations weren't just mistakes.
Interesting. He even questioned the argument that following SEU would lead to long-run success.
He did, yeah. He said that the specific choices you make matter, not just the average outcome over time.
I see. But he did seem to accept that some kind of consistency was important for rationality.
He did. Yeah, at least weak order and stochastic dominance. Then there's the famous case of Savage himself and his own experience with the Allais paradox.
Right. He initially had those Allais preferences too, didn't he?
He did, yeah. But then, after thinking about it more, he changed his mind, saying his initial preferences were errors.
So by reflecting on the axioms, he was able to correct his preferences.